Thanks for the invitation, and thanks for all of you who survived. Great. So the goal of my talk is to talk about the Aldous-Lyons conjecture. And the title is Subgroup Tests and the Aldous-Lyons Conjecture. And this is a joint work with Louis Bowen, Alex Lubotsky, and Thomas Vedek. And the way the talk is structured, the two talks is structured is that I'm going to start with some motivation. Then I'm going to talk about invariant random subgroups and the Aldous-Lyons conjecture. Afterwards, I'm going to talk about our tool of refuting the Aldous-Lyons conjecture, which is subgroup tests. And this will require us to talk about complexity theory and things from theoretical computer science. And finally, I'm going to talk about non-local games, which will require us to talk about a bit about the foundations of quantum mechanics. So I hope you will have a good time with all of that. So let me start with the motivation. And my motivation will just be 3 open problems. Okay, so let's start with the first one. So the first one is called direct finiteness. It's due to Kaplansky from the 60s of last century, previous century. Yeah, so what Kaplansky was very interested in group algebras. So let's just recall what a group algebra is. So you have a field, and you have a group, and you can just look at linear combinations of group elements with coefficients from the field. And then this is a nice ring. You can ask questions about the structure of the ring, and Kaplansky was interested in that. And one of the questions he asked is whether the following always holds. Okay, so that's the Kaplansky conjecture. Does alpha times beta equal 1 implies beta times alpha is equal to 1. So we're used from matrices that this is true. Okay, so the finiteness is maybe finite dimensionality in this context. Okay, does left invertibility in the group algebra implies right invertibility and vice versa. Okay, so that's the first open question, and this is still wide open. We don't know either refutation of this thing or proofs of this fact. Okay, second problem. This is, I'll call it the group extension problem. Group extension problem. But essentially, it's always called the Kerver-Laudenbach conjecture. So Kerver and Laudenbach. And it's also mid-20th century. I only found citations of the problem, not the original, like where it was originally asked. And all of them were from the 60s again, so I don't give you a specific decade even. And what the question is, okay, so we are used to, from like the most basic fact in Galois theory is the following. If you have a polynomial of positive degree, a univariate polynomial of positive degree, implies that there exists some field extension of f, right? There exists some E containing f, and some element in E which is a root of this polynomial. Alpha in E, such that the polynomial evaluated at alpha is 0. Now you can ask the same type of question in groups. So you need an analog of the notion of a polynomial, and that would be a univariate word. So let's define something. Definition. A univariate word is of the form so it has a single variable, x, and this is w for word. And it's of the form gamma 0 times x to the n1 times gamma 1 times x to the n2 dot 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 gamma k minus 1 x to the nk times gamma k. Okay, where the gamma i's are from some fixed group, like here. Okay, so I have some group gamma, And the ni's are just integers. Okay, so, and x is my variable. So you should think about it similar to polynomials. Okay, this defines some equation. I can say equal to 1, and I ask what are the solutions to this equation, right? In a single variable equation over a group. Okay, let me swap these two things. Oops, the other way around. Okay, great. Now, the natural question, so I'll write it here, is does there exist a group delta that contains gamma such that there exists an element alpha in this larger group delta for which the word, when you plug in alpha instead of x, gives you the identity element? And the answer to this question is no. Okay, and it's actually very simple to find words that no matter how much you extend the group, you don't have solutions to this word equation. And that's just the following. So take the following word, ax, bx inverse, and take a and b to be some two elements not of the same order. So for example, take a to be the swap between 1 and 2 inside the permutations, and b be the cycle of length 3. And now, what does it mean to find some x that makes it equal to 1? It's the same thing as showing that a and b are conjugates. So actually, a inverse is conjugate to b. But this cannot happen. They have different orders. If you have two elements of different order, they can't be conjugates of one another. So,
in this case, you also have the wrong parity.
What?
Here you also have the wrong parity.
The wrong parity. Okay, yeah. That's true. Yeah, you're right, in this specific example. But in general, you could take any two non-same order, and you'll see that. So Kerver and Laudenbach said, OK, that's essentially the only obstruction. And what is the obstruction in this case? Just that the sum of exponentials is 0. So the Kerver-Laudenbach conjecture is question is true when the sum of ni's is not 0. And sum on ni's is what happens here. Great. So we have our second problem. Let me give you a third problem. Probably they are all false, but please, Peter, show this to us. I have no idea. I have no idea. No, you're right. I could have called them problems. When I'll get to the Aldous-Lyons conjecture, I know that it was phrased as a problem, but in this context, I really don't know. I think that Kaplansky genuinely conjectured, but regarding Kerver and Laudenbach, I have no idea. OK, third problem. That's like algebraic eigenvalues conjecture. Algebraic eigenvalues conjecture. And it's due to many people. So this is Dodziuk, Linel, Matai, Schick, and Yates from 2003. And they asked the following question. OK, so let me give you first the context and then the question. So the complex group algebra acts naturally on square summable functions from the group to the complex numbers, right? And inside this group algebra, there is the integral group ring, right? Contained here. There's just Z gamma. Now, just a quick remark. So these are bounded. These act as bounded operators. Bounded operators. And just a quick reminder. A number, complex number, is an eigenvalue of a bounded operator if lambda times the identity minus the operator is non-injective, is not injective. So we talked about spectrum all the time. Spectrum means this is not bijective, but a stronger condition is the fact that this is not injective. Some operators have eigenvalues, some operators don't have eigenvalues. Great. So Duke, Linnell, Matai, Schick, and Yates asked the following question. Are all eigenvalues of alphas that come from the integral group ring algebraic? Meaning they are in the algebraic closure of the rationals. Again, open problem. Whoops. Now you should ask yourself, okay, that's nice. You gave us 3 problems. It's nice to learn about open problems in mathematics, especially old ones. Why should we care? We should care because of the following fact. All of these problems are true for a specific class of groups called Sophic groups. So I didn't say what are Sophic groups. I will define them at some point in this lecture. And these are due to 3 different people. So, okay, direct finiteness was shown by Gromov in 1999. So for Sophic groups, it's known by Gromov. This is known by Pestov in 2008. And this is due to Andreas Thom in 2008 as well. That at least for Sophic groups, these things are true. And that's why I asked Peter to show me that these things are false, because in particular, it will show us that there are non-Sophic groups, and this is still an open problem by itself. So this is a problem. Are all groups Sophic? So we know what Peter thinks. No, because he doesn't believe even those conjectures. And I'll say most people think the answer is no, but no, I want you to keep this, this idea. Yeah, so this just shows our ignorance, because I think most people think there are non-Sophic groups. And I think most people will bet that at least one of these conjectures is probably wrong, but we as a community don't know even to touch a single non-Sophic group to show that a single group is non-Sophic. And that's essentially the topic of today. I'm going to talk about some generalization of the notion of a non-Sophic group, and show you that there exists some generalized non-Sophic object. Okay, so to that end, I'll move to the second topic of my talk, which was, if you remember, invariant random subgroups and the Aldous-Lyons conjecture. I think I'll swap the boards because there it looks better, right? I'll start with the deeper one. Great, so invariant random subgroups and the Aldous-Lyons conjecture. So throughout this talk, S will be just a finite set. And I denote by f of S the free group with basis S. And Ramon reminded us what is the free group with basis S. It's just all words in S and formal inverses of S, right? And once you have a group, you can just think of all its subgroups, just collect all its subgroups as a single space. The subgroups of the free group. And these subgroups have a nice topology on them, just the product topology, which makes them into a compact space. But at least in this context, this is usually called the Chaboty topology. And there is a nice metric that just gives you the topology on the subgroups, which is the following. The distance between a subgroup H1 and H2 is 2 to the minus R, where R is the shortest length of shortest word. And the symmetric difference between H1 and H2. So I just asked, what is the word that sits in one of them and not in the other? Which one is the shortest one? This is R, like the length of it is R, and the distance is 2 to the minus R. This is a compact space with respect to this topology. Great. Now I'm going to talk about invariant random subgroups, so I should define what a random subgroup is. Now that we have a compact space, nice compact space. Random subgroups. These are just Borel probability distributions over the space of subgroups. Great. As a visual aid, it will be helpful for us, and also that's the way I usually think about all these probability distribution, is thinking about them as sampling mechanisms. Okay, so I will think of a random subgroup just as some black box with a button on top, and whenever I push the button, I get as an output a subgroup H distributed according to the appropriate probability distribution. Sampled according to the appropriate probability distribution. Great. Now, the random subgroups, so let me just give them a notation. So these are probability distributions over subgroups of the free group. So they also have a natural topology on them. That's just the weak star topology. And again, I can just say weak star topology, but let me give you like a down-to-earth description of the weak star topology, at least in this context. So a sequence of random subgroups, weak star converges to another random subgroup, if and only if, for every finite set K in the free group, the intersection of pi n with K, this is a sequence, converges to pi intersection K. Okay, and this is only for finite subsets of the free group. So I reduced the definition of the weak star topology to saying what is the intersection of a random subgroup with a subset, but that's not that hard. This would be pi intersection K. This is the original pi. You sample according to pi, you get a subgroup. You intersect it with K, you get H intersection K, which is a subset of K. Right? So this is, in total, a probability distribution over 0, 1 to the K, but this is a finite space, right? So these are essentially just vectors of numbers between 0 and 1 of 2 to the K length. And we understand what does it mean for a sequence of vectors to converge to a specific vector. Right? This is the usual Euclidean metric, for example. The point is that this is for every finite set K. Okay, great. Now, another thing that you can do with random subgroups is similar to subgroups. You can conjugate them. And again, I'm going to use the sampling mechanism picture. So what would be the conjugate of pi by some element from the free group? It would be first sample according to pi a subgroup, and then conjugate whatever you got out of it, right? So this is a priori a new sampling, no, it's always a new sampling mechanism, but it's not clear that this is a new distribution over subgroups, right? And we will say that something is invariant random subgroup, so we define it here. So pi, a random subgroup is an IRS, an invariant random subgroup, if for everyone, shouting, sorry for that, maybe I'll put it a bit lower. Great. If for any element in the free group, the conjugate of pi is the same as the original pi. Okay, we denote the collection of all such probability distributions by IRSs of the free group. Great, so this is a generalization of the notion of a normal subgroup, right? Like normal subgroups are just deterministic subgroups that are conjugate invariant. This is the probabilistic version of a normal subgroup. And thus, the first example of an IRS, well, let me give you some examples. If there are any questions, please stop me. Like I'm kind of running away, but I feel that it's still very basic. So please stop me if you need. So some examples. So the first is just the normal subgroups themselves. Normal subgroups. So what do I mean by that? I mean Dirac measures, right? Like you take the black box, which is just the Dirac measure on some subgroup n. It always outputs n. And because n is conjugate invariant, you can conjugate it however you want. You will always get the same n. Great. Second example, which is just a really small generalization of this idea. Say that you look at the conjugation orbit of some subgroup. So you look at all WH, W inverse, such that W is an element of the free group. So every subgroup has a conjugation orbit. Some of the subgroups have a finite conjugation orbit. So if the size of OH is finite, then a uniform element from it is an IRS. And I hope this is clear. Every conjugation will just permute the orbit somehow, and like the uniform distribution is invariant under permutations. Great, let's take this upstairs. Now the third example is the most important for me. That's actually the class of IRSs that I really care about. And these are the finitely described IRSs. Finitely described IRSs. So how do you define them? You take some finite set omega. You take some action of the free group on the set. Now, whenever we have an action of a group on a set, we can define the stabilizer of a vertex, right? For every element from omega, we can define the stabilizer of this element to be all group elements that fix this specific element. And now we don't have much freedom. We will just choose a uniform vertex and output its stabilizer. So I'm describing it as a sampling mechanism. Sample x in omega uniformly and output the stabilizer of x. So this is a very nice collection. I'll take it a bit upstairs. This is a very nice collection of invariant random subgroups. So we'll give it like a notation. These are IRSs finitely described of the free group. Now, a very simple observation, maybe I'll just won't do it like this. So this is just this collection. And it's very clear that you can do the weak star closure of this set, right? This is contained in the finitely described IRSs of the free group, weak star closure. And because the IRSs are closed by themselves, this is just contained in the collection of all IRSs of the free group. And it's not very hard to see that this is a strict inequality. Can someone give me an explanation why this is a strict inequality? Okay, so let's start by the fact that this is a countable set, for example. So even if you take convex combinations of them, you get something new, and the closure will, for example, contain the convex combinations. But let me give you a more interesting example. Okay, so let Fs, it always surjects onto Z to the S, right? You have some normal subgroup here. It's an infinite index subgroup, so it will never be supported in this thing. So the support of all these things are always finite index. But I claim that this thing, the Dirac measure on this normal subgroup lives here. So that's an exercise. If you've never seen it, it's not a bad exercise. Great, so we see that this is a strict inequality. So the finitely described IRSs are strictly contained in their closure. But Aldous and Lyons asked, so Aldous-Lyons conjecture, I'll just write ALC throughout the talk. That's from 2007, I think, or even 6. Is the right inclusion and equality. And as Peter said, I say conjecture, although this was phrased as a question, but I will say that David Aldous himself in his website calls it the Aldous-Lyons conjecture and phrase it as a question. But from now on, the yes answer to this thing, I will just call the Aldous-Lyons conjecture. Okay, so when I say if the Aldous-Lyons conjecture is true, I mean if this is an equal sign. Okay, great. So any questions up until now? This is the conjecture I'm going to talk about. Not too much, but I'm going to relate it to the open questions from the beginning, at least. So first of all, let me just give. Yeah. So for example, if you have, but I will get to that. Thank you. But these will be parts of my remarks in a moment. But I just want to give a name to this set. Okay. So if the conjecture is at least like you parsed it, great. I'll remark about it in a moment. So these are just called the co-Sophic IRSs. And I want to give 2 remarks. One is related to what Peter just said, and the other is related to this name. So remarks on the Aldous-Lyons conjecture. Remarks. So my first remark is the following. If you have a finitely generated group gamma, then there exists a set S such that, finite set, such that the free group surjects over S, surjects onto gamma, right, by definition of being finitely generated. Now, if you have such an epimorphism, you have a kernel to this epimorphism. And the following is either a claim if you know what a Sophic group is, or a definition if you don't know what a Sophic group is. This group will be called Sophic if and only if the Dirac measure here is co-Sophic. So it's in this week's star closure. Okay? So in particular, the takeaway from this is conclusion. The Aldous-Lyons conjecture implies all groups are Sophic. And that was a bit of a big divide. So actually, as Peter remarked, people in probability theory, some of them thought that the Aldous-Lyons conjecture should be true because of some heuristics in their field. But when you show it to a group theorist, and you tell them that the Aldous-Lyons conjecture implies that all groups are Sophic, usually they say, yeah, OK, so it cannot be true. So it's kind of like there was a divide between the fields, whether it should be true or not, or should not be true. So that's my first remark. And again, like you can take it as the definition of a Sophic group. Any questions about that? No? Perfect. My second remark is that usually people don't phrase the Aldous-Lyons conjecture this way. Like, I think 90% of people that heard about the Aldous-Lyons conjecture before heard it in a completely different manner. So let me formulate the usual one. The question is, are all unimodular random rooted graphs the Benjamini-Schramm limits of finite ones, finite graphs. And I won't explain what is unimodular, but I will give you at least a dictionary between our formulation, the one that I wrote there, okay, and this formulation. Okay, so what is the dictionary? So first of all, every subgroup defines a Schreier graph, and the Schreier graph is naturally rooted, right? So H maps to Schreier graph of the action of Fs on H, rooted at the coset of the identity at H, identity times H. Okay? So this is the first part. And then, okay, clearly an IRS is at least, okay, maybe a random subgroup. So a random subgroup is a random rooted graph. But it's not any random rooted graph. It's a random rooted Schreier graph. Now, this is the following thing that I'm going to say is a theorem. I didn't even define to you what is a unimodular random rooted graph. But if you start from an IRS, you get a unimodular random rooted graph. Okay, and this is due to Abert, Glasner, and Virag from their famous paper that even defined this notion of IRSs. Great, and now, what were the finitely described IRSs? They were just actions of the free group on some finite set. This clearly defines a finite graph, right? You see that? Like the vertices are omega, you connect x to y if a specific generator S from S sends x to y, okay? You get some graph out of it. So finitely described IRSs map to finite graphs, finite Schreier graphs again, Schreier graphs. And just I need to define that weak star is the same as Benjamin-Ishram limits. Okay, like it's just a different name for the same topology. Okay, so we can see from the dictionary that are all unimodular, random, rooted Schreier graphs. The Benjamin-Ishram limits of finite Schreier graphs is what I formulated there. But I'll just say as a fact, so maybe I'll take this upstairs. I'll just state it as a fact. The Schreier version, refuting the Schreier version, implies refuting the unoriented, unlabeled version. And this is essentially an exercise. This is usually called the decoration trick. So just see that you can implement orientations and labels using some things that don't have labels and orientations, right? That's what it says. Great. How much time did I have for the first one? 25. Perfect. I'm in good shape. So regarding just Peter's remark, if you, like, the reason they cared about this stuff is because, for example, if you take planar finite graphs and you look at their Benjamin-Ishram limit, then the random walk on this object is recurrent. Okay? So somehow we know that, like, the simple random walk on the two-dimensional grid is recurrent, right? Like the probability that you come back to your starting position is 100%. And like somehow the Benjamin-Ishram limit remembers the planarity of all the things in the sequence, okay? And through this idea of recurrence. So that's why they cared about these kind of things. Like somehow the Benjamin-Ishram limit moves you, you hope that some properties of the finite graph just move to the Benjamin-Ishram limit. And then this unimodularity, they asked, is this specific property of unimodularity essentially just comes from the fact that you're the Benjamin-Schramm limit of finite graphs, or is it something which can be acquired without being the limit, Benjamin-Schramm limit of finite graphs? That was a question. Okay, great. Do I want to say anything more about that? Let me just check. No, we can move to the next part of the talk, which is subgroup tests. So where do I want to start it? Maybe let me leave this formulation, just hide it. And I'll try to work with these two boards. I didn't say the most important thing, theorem. This is Bowen, Chapman, Lubotsky, Vidic from last year, end of last year. No. So the Aldous-Lyons conjecture is false. There exists something, so I'll raise the board again. Sorry for that. There exists something here that does not exist here. This is not an equality. There is a strict inequality, like strict containment between these things. So I'll write it that way. No, there exists a non-co-Sophic IRS of the free group. So it's not as good as a non-Sophic group. So if you had a non-Sophic group, that would already prove that. Because what is a non-Sophic group? It's a Dirac measure here, which is not here, right? So we weren't able to find a Dirac measure here, which is not here. We were able to find something here, which is not here. So the sophicity problem is still open. Okay, great. So how do we do it? How do we prove that there is some non-co-Sophic IRS? We use complexity theory, essentially. Now, we're going to move to theoretical computer science now. So subgroup tests. Now, to explain what are subgroup tests and why they are motivated, I need to start with some basic stuff. So what is a decision problem? So a decision problem is the following thing. Given a combinatorial object, and I'll write in parentheses, but this is extremely important, encoded as a bit string, does it have a specific property? Now, this is intentionally vague, okay? Because I want it to be very wide. The collection of decision problems should be very wide. But let me give you just some examples which are standard ones. Given a finite simple graph, is it three-colorable? So can you associate colors to the vertices of the graph such that no edge is monochromatic? Right? Second thing, given a Turing machine, does it halt on the empty input, for example? Single input Turing machine, empty input. Third type of problem, given a finite presentation of a group, so just generators and relators. Is it trivial? Is it isomorphic? To the group containing a single element? Okay. Now, quite famously, this is an NP complete problem, and these two are undecidable. They are actually equivalent to one another. And there is no algorithm that in finite time will decide whether you are in one of these situations. Great, but the type of problem that so my goal is to define to you, yeah. Yeah.
What are you doing?
Well, okay, let's get to that. Like you're right that
Three
Okay, no, they are not different. That's wrong. They are decision problems. Okay. You mean that clearly, no. You mean that clearly this can be decided, first of all, and not only it can be decided, it is part of something which can be like somehow decided efficiently given that I have a witness, which is exactly saying that it is in NP, which is a complexity class. And quite famously, these two decision problems, not only you cannot in efficient time decide them, or like efficient time decide them with some hint, even in infinite time, like no matter how much time I'll let you, won't be able to resolve them. So usually these are called computational classes, where these live. But we will see that exactly the result is some mixture of these two things, so I will need complexity at some point. That's a good remark. Okay, but my goal is now to define to you, okay, I prefer to start from the other board. My goal is now to define to you a special type of decision problem. It's not the standard one. It's called a gap problem, or a promise problem usually in computer science. So let me call them a gap problem. And here we start with a combinatorial object, and we want a yes-no answer for it, right? Here we start with some error parameter theta, and some function which we call the value from all possible combinatorial objects that we care about. So either all graphs, all Turing machines, all something, to the numbers between 0 and 1. So even to define a gap problem, I need to first choose a positive number and choose some value function from combinatorial objects that I care about to 0, 1. And then what would be the gap problem? Given a combinatorial object, is it value 1? Is its value equal to 1 or strictly smaller than 1 minus theta? Now, the first thing you should tell me is why should it be either that or that, right? Like a priori, I start with combinatorial objects. I send them to 0, 1. Some of the objects can be sent to the interval between 1 minus theta and 1, right? So the whole point of a gap problem, as I said a moment ago, also called promise problems, is that I promise to you that whenever I give you an instance of the problem, it's either in this category or in this category, or other way to say it. If for some reason I gave you something in between, you don't need to guarantee anything. You can do whatever you want. You can answer whatever you want. I don't care what happens if I give you something in between, only if I give you 1 or strictly smaller than 1. You need to differentiate between these two cases. Now, again, this shouldn't be clear. It's like a general problem. So let me give you an example. Okay? And the example would just be the gapped version of 3 coloring. So again, just for the example, let theta be 0.01. And if I have a coloring from the vertices of some graph to 1 to 3, so that's a supposed 3 coloring of the graph. 5 minutes, thanks. Tell me also when I need to stop. I'll just stop. OK, so we have a coloring from the vertices of some graph to 1 to 3. An edge xy is C good if its endpoints are different. So these are all the edges which are non-monochromatic in this coloring. And then you can just define the value of this graph G versus this specific coloring C to be the number of good edges divided by the total number of edges. So if there is even a single edge in the graph, clearly this can be 0. Just color all the vertices by the same color, and then this would be 0. Agree? But this is not that interesting. The fact that there are bad colorings is not very interesting. Usually what we care is somehow optimizing this, finding the best coloring. Okay? So the value of the graph itself would just be the supremum over all possible colorings of the value of the graph versus the coloring. And I hope that you see that this value is 1 exactly when the graph is 3-colorable by definition. Okay, great. Okay, great. And then the gap 3-coloring problem, parameterized by 0.01, is the following. Given a graph, is it 3-colorable, or does every coloring have at most 99% of good edges? And again, I hope it is clear that this is an easier problem than 3-coloring. Here I promise to you something. The instances that I give you are either colorable or highly non-colorable, right? Like they cannot pass this threshold of 99% of the edges being satisfied. So it's, I don't know if it's surprising to you, but it should be surprising to you. And this is one of the biggest achievements in theoretical computer science. This is called the PCP theorem, the probabilistically checkable proofs theorem. And it says that this problem is as hard as 3-coloring. 3-coloring 0.01 is NP complete. What do we mean by that? There is some mechanism of taking a graph, G, translating it in polynomial time to a graph G prime. So this graph is not much larger. It's only polynomially larger than the original graph. And they have the following property. If this was, so this is called completeness. If G was 3-colorable, G is 3-colorable, then so is G prime. And soundness, if G is not 3-colorable, then G prime is highly non-3-colorable. Highly non-3-colorable, which I mean its value is at most 0.99. Okay? And the whole, okay, one of the celebrated proofs of the PCP theorem is genuinely thinking of this as a combinatorial operation that takes polynomial time. But there were previous proofs that worked a bit differently. Okay, so I'll just say that my goal in the next hour would be to define these combinatorial objects that I called subgroup tests, associate a value to them. Once I associate a value to them, I have some gap problem. And the whole idea is to relate the gap problem to the Aldous-Lyons conjecture. So that's what I'm going to do in the next lecture. Hi, everyone. Thanks for coming back. So I was asked during the break whether I'm actually going to use this. So the answer is no. I'm going to use only ideas from the proof of the PCP theorem, actually earlier version of it called the MIP is equal to NEXP equality by Babai, Fortnow, and Lund. But I won't get into it because I won't have time to get into it anyway. OK, so I said that I'm going to define a combinatorial object called a subgroup test such that some gap problem about it is related to the Aldous-Lyons conjecture. So let's do that. Let's define our subgroup tests. So a challenge is just a pair, K comma D, where K is a finite subset of the free group, and D is a function from subsets of K to 0, 1. Now, I call it a challenge because it challenges subgroups. So we say that a subgroup H wins the challenge if and only if you evaluate D on the intersection between H and K. So the intersection between H and K is some subset of K. I can evaluate D on it. If I get 1, I said that the group wins the challenge. If I get 0, I said that the group loses the challenge, lost the challenge. Great. Now what is a subgroup test? So to define a subgroup test, you need to give me a finite set, which will just be the generators of the free group. You need to give me a tuple, a sequence of challenges. Ki, di, I goes from 1 to m for some finite number m. And you need to give me some distribution mu, which is a probability distribution over the numbers between 1 and m. So it's just a distribution over the challenges. Now, again, this is a combinatorial object by definition. You need just a finite bit string to define it, at least when this distribution is rational, right? But usually, this object is thought of as the rules of some interaction between a referee and an invariant random subgroup. So it's a test for an invariant random subgroup. Let's think about it in the following way. So we have a referee. It has access to its own distribution over challenges, mu. And it gets access to some IRS, pi. Now, what will the referee do? It will run the subgroup test. It will push the button on mu. It will push the button on pi. It will get some subgroup H here, some index I here. And then we know that it needs to check whether the subgroup H wins versus the ith challenge. So it's essentially going to evaluate the I of H intersection Ki. So again, you don't need to think about it that way, but that's a good mental image of why we even defined this tuple. This tuple exists as a combinatorial object by itself. Okay, I wanted to use this thing, right, for the time being. Now, similar to the coloring case, given a specific IRS pi, I can just ask what is the probability that this will be 1 given that we run this subgroup test T. So I didn't give it a name. T would be this upper tuple. So given that you use pi versus this subgroup test T, what is the probability that the output here will be 1? Okay, that will be the value of pi versus the test. And you can write it down. It's just the expectation, the double expectation when you sample I according to mu and H according to pi of the I H intersection Ki. Right, that's by definition. But remember that the value that we had before for the graph case was not the value of the graph versus a specific coloring. It was some supremum over all possible colorings, right? So here we have two choices, right? We have the invariant random subgroups, and we have the finitely described invariant random subgroups. And we can take the supremum over both. So we get two different types of values. So you can define the ergodic value of the test to be the supremum over all pi's, which are IRSs, of the free group of the value of the test versus pi. And you can define the Sophic value of the test to be the supremum over all pi's in the finitely described IRSs of the value of t versus them. Now, clearly, this is a larger set than this. So it's clear that this thing is larger or equal. Sorry, not here. This thing is larger or equal to this thing. You agree with that, right? I'm taking a supremum over a larger set. But what did the Aldous-Lyons conjecture tell us? It told us that this set is dense in this set. And if you check for a fixed t, if you fix t and run over the pi's, this is just a linear functional, continuous linear functional from the IRSs. So if something is dense in something and you evaluate the continuous function, the supremums must agree. So just a quick corollary. Write it here. So a quick corollary. If the Aldous-Lyons conjecture is true, then the ergodic value of every test is equal to the Sophic value of every test. That's just what we just said. Great. So now let me explain to you how do we refute the Aldous-Lyons conjecture. That requires two theorems. Okay? So, before I say the two theorems, we now have a notion of a value. The correct notion of value for us will be the Sophic value. Okay? And we can define the gap problem associated to the Sophic value. So Soph val theta would be given a subgroup test T. Decide whether the Sophic value of T is 1 or the Sophic value of T is strictly smaller than 1 minus theta. So this parameter theta is here. Great. Now I can tell you the two theorems that we actually prove. The first theorem is the following. So that will be theorem 1. The Aldous-Lyons conjecture implies that Sophic value theta, so for every theta larger than 0, Sophic value theta is decidable. Namely, there exists some algorithm that will halt in some finite time that will, if the Aldous-Lyons conjecture is true, there is some algorithm that in finite time can distinguish between these two cases. Maybe will take a long time. We have no guarantees on the amount of time, but it will halt and answer one of these. Second theorem. There exists a computable, and I will just remark, we can show that this is actually efficiently computable, but to deduce what we need, we don't need the efficiency here. So, Peter, to your remark, at least here in this theorem, I don't need the word efficient, but in later things, we would need things to be efficient. So there exists a computable mapping from the set of all Turing machines to the set of subgroup tests So I'll just give you a notation. It's not enough subgroup tests. Subgroup tests, comma, positive rational numbers. Okay? So I'm going to give you, given a Turing machine, a subgroup test and a positive number. So M maps to T of M, theta of M, such that okay, I'll just keep writing here, such that completeness, if M halts, then the Sophic value of T of Tm. So I computed from M some Tm. The Sophic value of Tm is 1. And soundness, if M never halts, then the Sophic value of M, of Tm, I know that it's bounded by 1 minus theta M. Okay? And I hope that it's clear to you that the corollary of these two things, corollary, okay, blue is very bad. Anyway, it's hard to see. So corollary, the Aldous-Lyons conjecture must be false. Let's see why. If the Aldous-Lyons conjecture was true, I can decide the halting problem. How would I do that? I will start with my Turing machine. I will apply this computation. I will get as output two things. One is a subgroup test, and one is a parameter theta m. And then theorem 1 said that no matter what theta is, I can decide Sophic value of theta. So I can just, whatever algorithm I'm guaranteed to have here, I will run it with the error term theta m. And in some finite time, I will be able to say whether m halts or not. Okay, but Turing showed us that the halting problem is undecidable, so the Aldous-Lyons conjecture must be false. Okay, so that's the structure of our proof. Any questions about that? Yes? Wait. Yeah, like on the empty input, yeah. Yes, here I'm giving you the encoding of some single input Turing machine. I'm producing some subgroup test, comma, some rational number. I actually can do it in efficient time, so if the description of the Turing machine is of some side, this thing will be polynomially larger. So usually when you say the halting problem, you ask whether a single input Turing machine halts on the empty input. Yes, so the only thing is the machine M. I'm calculating from the machine M the description of a subgroup test and some rational number, such that if the machine halts, the Sophic value of this test is 1, but if the machine doesn't halt, the Sophic value of this test is bounded by 1 minus this error term. Yes, but the theorem says that no matter what theta you give me, I have some algorithm that will decide. So it's essentially an algorithm which has a parameter theta. And you can plug in the theta as one of the parameters of the problems, and then. Yeah. It is. You're right. It's a bit lying here. It's a single algorithm with some parameter theta that solves each one of these specifically. Thank you. That's actually a good remark. Any other remarks? No. Okay. So in the rest of the time that I have, my goal is to at least explain to you some things about Theorem 1 and Theorem 2. So Theorem 1 would be kind of easy to explain. Theorem 2 will require us to talk about Theorem 3 and Theorem 4, and it will cascade on, like turtles all the way down. Okay, so let's say some remarks about Theorem 1. Sorry that my board is so messy. Okay, great. So remarks on Theorem 1. So let me tell you what we actually prove. Okay? So say that you have a test. A priori, it can have an ergodic value which is strictly larger than the Sophic value. We don't know. That's if we can just show this directly, it will refute the Aldous-Lyons conjecture, because we said the Aldous-Lyons conjecture says these are the same things. These two are the same thing. What we do is essentially just devise two algorithms. One of the algorithms approaches the Sophic value from below, so it will produce a sequence of numbers that get larger and larger, or at least not smaller and smaller, so a non-decreasing sequence of numbers that in the limit will approach exactly the Sophic value of the test. And we provide another sequence of numbers, so another algorithm that produces another sequence of numbers that approaches the ergodic value from above. Okay? And I will just remark, this is a naive thing, okay? Like, just tell me what is the algorithm. The Sophic value is the supremum over finitely described IRSs. What did we say about the finitely described IRSs? That they are countable, right? So just enumerate them somehow, check one by one what is their value, and you will get something that approaches the Sophic value. Agree? Great. So this is naive. This is just brute force. This is slightly more interesting. This requires some linear programming. What do I mean by that? We generate a countable sequence of linear programs that give you numbers that are smaller and smaller, such that in the limit, you get the ergodic value of t. And I'll explain in a moment how do you do that, but just how do you deduce Theorem 1 from this? The picture in Theorem 1 is just that this is a single line. And you can run the yellow algorithm. You can run the purple algorithm. And for every theta that you have, just halt when the distance between these two curves is smaller than, for example, theta over 2. Actually, theta is enough, but theta over 2 is like surely enough. So I hope this is clear that once you have these two things, if the Aldous-Lyons conjecture is true, we have theorem 1. So let me just elaborate a bit about this upper yellow algorithm. Okay? So what are we trying to do? We're trying to optimize over the IRSs, right? Now, the IRSs are complicated, but we don't need to study that. They live in an infinite dimensional space. But actually, for a subgroup test, I don't know if we have it on the board. So a subgroup test was S, Ki, Di, and some mu, right? These Ki's are just finite sets, and we have finitely many of them. We can just take K to be the union of all the Ki's. And then to decide what is the value of a specific IRS, we don't need to know how it samples subgroups. We just need to know how the subgroups that it samples intersect the specific K. So we can actually look at the following convex subset. So IRS, you take IRSs of the free group, you intersect them with K. This is a convex set in R to the 0, 1 to the K. Agree? These are just probability distributions over subsets of K. So this is nice. This is a convex set. Now, how do we generate the linear programs? We just outer approximate this convex set using polytopes. You just start adding hyperplanes to this thing, define half spaces, right? And at some point you get, like, you can start with something compact, actually. You can start from the cube of all possible probability distributions and add these spaces. So you get smaller and smaller convex polytopes. And just finding the optimum of a linear functional over a polytope is what's called a linear program. Okay? So by definition, we're running linear programs, and there are either efficient or non-efficient algorithms for this. You don't really care. You just calculate them one by one, and the whole point is that you can add a countable amount of half spaces, like the intersection of countable amount of half spaces, that gives you exactly this intersection. And I will just say that the intuition is the following. Like, look at random subgroups that are not necessarily invariant, but they look invariant on larger and larger balls in the free group. And that's all. I told you what are the linear, like, what are the half spaces. So each half space you get from bigger and bigger restrictions when you get this ball larger and larger, essentially. Okay, any questions about this? No. Okay. Let's keep moving on. I'll take it upstairs. Huh? Still no complexity. Yeah, you're right. But there were linear programs. You believe in linear programs. Okay, great. So now I need to say some remarks on theorem 2, right? Because the fact that this was that easy and that we wrote 250 pages about this stuff means that theorem 2 is hard, or at least harder. Okay, so remarks about theorem 2. Remarks on theorem 2. Okay, so as I said, essentially the way I'm going to explain to you the way we prove theorem 2 is by stating two new theorems, which is kind of a hack, but you will see why it's interesting. So theorem 3 states the following. There is some other collection of combinatorial objects called tailored non-local games. Maybe I'll take it further up. So I have this larger, another collection of combinatorial objects, tailored non-local games. And there is a mapping, again, efficiently computable mapping, to subgroup tests, which is value preserving, or actually it's essentially value preserving. Well, I won't explain exactly what this means. Essentially, I lose something in this mapping, But at least if this thing has, so I didn't explain what is this thing, but I just claimed similar to before, we have a combinatorial object, we can associate some value to it. In our context, that there are, actually in this case, there are at least 6 different values that people care about in this world. But one of them that we defined is called the ZP value. And another, which is much more common, is called the quantum value. And I will need in a moment that the quantum value is always larger or equal to the ZP value. Okay? And that value preserving map sends ZP value 1 to Sophic value 1 here. And it sends things that are far away from 1 to things that are far away from 1, but you pay some price, which depends on the size of the encoding of this thing or whatever. I won't get into it now. But you lose something along this thing. Right, so this is theorem 3. What is theorem 4? It will look almost the same as theorem 2. There exists a computable, actually efficient mapping from Turing machines to tailored non-local games such that completeness, if M halts. So let me just give notation again. So the Turing machine M is sent to the tailored non-local game G of M. So if M halts, the ZP value of GM is 1, and soundness. Notice that here I have only a game and not a game and a parameter. You will see in a moment why. The soundness is if M never halts, then actually the quantum value, so it's usually denoted like this. This is usually denoted like this, and this we usually denote like var ZP. The quantum value of the game is bounded by 1/2. Great, okay, so we had some progress. I hope that now you see that theorem 3 and 4 imply theorem 2. Let's see why. You just compose these 2 maps. Okay, you start from this map, you map this thing, and then you map this thing. And because we understand well how much do you lose along this mapping, and actually here we do use the fact that this is like, we can control the time here because this is related to how much we lose in the second step. We can actually calculate what is theta M there on the right-hand side. Okay, so that's just a composition of 2 maps. Now you should say, okay, he's like doing a trick, because now the way he's going to prove this is by adding another map and adding another map or something of this form. But that's not true. And the reason for this is that actually if you drop here the word tailored, if you remove here the word tailored, and you remove here the word ZP and move back to the quantum value, this is a known theorem. Okay, this is called MIP star is equal to RE. This is due to G, Natarajan, Vidic, Wright, UN from 2019. And they showed that if you drop tailored and you use the quantum value here, then this is true. So you should be much happier, just a moment, Peter. You should be much happier when you get to this kind. So once we saw this thing, so we first saw this thing, and then we were extremely happy because now we at least knew that maybe some tinkering of this theorem will enable us to deduce what we need. Okay? What do I want to say? Yeah, now, Peter, your remarks. Multi-prover interactive proofs with that can share entanglement is equal to is as hard as the halting problem. So essentially, deciding the value of a non-local game is as hard as the halting problem, but this is exactly what I wrote here, right? So that's just a fancy name of saying the same thing. Okay, now, how much time do I have now? Yeah, okay, I'll get to it in a moment. But just how much time I have? Still 25. Okay, 21 minutes? How much is it? Yeah, 20 minutes exactly. Great. So I will just say that the reason that we got into all of this business was exactly because there is, actually so there are three categories of non-local games. There are all non-local games. Okay, maybe I'll draw it. All non-local games. Here's inside, there are the category that I mentioned. These are tailored non-local games, so it's a bit harder to reduce to a smaller set, right? That's part of the problem of this theorem compared to the original thing. There are the tailored non-local games. And inside this, there is an even smaller collection of games called linear constraint system games. It was known already, regardless of our work, like just from the MIP star is equal to RE and some various structure theorems about all these non-local games, that if you can reduce everything to the LCS games, if you can do theorem 4 and the target would be LCS games, there is a non-Sophic group in particular. So that's what kicked us in, like, and we thought, okay, maybe we can take the MIP star is equal to RE result, just change whatever is needed to change to get the LCS games, and we'll have a non-Sophic group. That failed. And not only that failed, William Slofstra and Paddock, one of his, I think, former PhD students, I think he finished, actually showed that there is some obstruction for doing that. Like, there is no simple combinatorial gadget that you can just plug in and it will make all the MIP star thing into a linear constraint system game. There is something deeper that you need to do, some smarter idea that you need to implement there. But I hope that you can see that at least this refutes, that's Peter's remark, this refutes some well-known problem of Alan Kohn called the Kohn's embedding problem. Okay, so if you prove theorem 4 without the Taylor, then only with the quantum value, it refutes a famous problem of Alan Kohn that asked, essentially, are all 2 1 factors limits of the finite ones, okay? In the appropriate sense. And I won't get into it. So we knew, okay, I'll at least give you some insights. We knew that Kohn's embedding problem has a specific formulation which is closely related to the Aldous-Lyons conjecture. You can formulate these 2 problems such they seem almost the same. And then we thought, okay, maybe there is some computational way to approach the Aldous-Lyons conjecture, and it worked out. And I'll just remark that we provided a completely new proof of theorem 4, like from scratch. We didn't like we didn't refer to the MIP star is equal to RE paper. We just wrote down everything again. And because this is a strengthening of the result, this also refutes Kohn's embedding problem. So you have two in one. You refute both Aldous-Lyons and Kohn's embedding when you do this work. Now I'll say one more general remark, and then I'll say something about theorem 3 and theorem 4. And to say that, I need to even define to you what a non-local game is because I didn't do that. So I'll start with defining what a non-local game is. Recently, a student from Waterloo named Aryan Mansour essentially showed, so theorem Mansour, 2005, he essentially showed that you can avoid subgroup tests completely. 25, thank you, sorry. I wanted to write just 25 and somehow I wrote the 20 in the beginning. Confused me. So what he showed, you can avoid subgroup tests completely. What do I mean by that? Instead of studying subgroup tests and associating something between non-local games and subgroup tests, just think of the non-local games. Think of IRSs directly as strategies for non-local games, and we will see what does it mean. And then you can just avoid, essentially, he uses many ideas of the way we prove theorem 3, but he essentially drops theorem 3 altogether. He uses just theorem 4 as a black box, and he's able to deduce that theorem 4, so what he shows, that theorem 4 implies both Kohn's embedding problem and Aldous-Lyons conjecture are false. So that's very nice. He simplifies some aspects of our approach, and I wanted to publicize it because, yeah, I think he He needs the publicity, and it's nice. Okay, so what do I want to tell you? Let's talk a bit about this. And to talk about this, let me give you a brief introduction to quantum mechanics. So I'll start with a very down-to-earth combinatorial definition of a non-local game, but then we'll elaborate and explain why is it interesting even. So what is a non-local game? It is composed of a directed finite graph, a function L from the vertices of the graph to natural numbers. For every vertex, you associate a formal generating set, Sx of size L of x. So this just tells me at each vertex of this graph what is the size of the formal generating set. It consists of a distribution mu over the edges of the graph. Wait. So you can think of it, it won't be the generators of a free group, it will be the generators of F2 to the Sx, actually, but we will see it in a moment. That's a good question, but these are just formal variables for now. And we need decision predicates. So for every edge, x, y, and e, we define a decision predicate that eats a bit string parameterized by s of x times a bit string parameterized by s of y. F2 is just a field with two elements for me. And it outputs either a 0 or a 1. So it outputs back a number in F2. Now, this is a hideous definition. Let me motivate it a bit, OK? So in the early 20th century, we discovered, we as humanity, that electrons have a magnetic property called a spin. Okay, so electrons behave like bar magnets with a north to some orientation and a south to some orientation. And when you want to measure this thing, okay, so you run it through something which is called the Stern-Gerlach apparatus. Stern-Gerlach apparatus. The electron flies through this thing, and it goes somewhere. So there is some magnetic field here, non-homogeneous magnetic field, and it will make, if a bar magnet is oriented up with north up, then it should go up. If a bar magnet is oriented with north down, it will go down. And if you have like a big magnet and you throw it and it's oriented like in between, then nothing should happen. So there should be, like for physical large objects that go through such a non-homogeneous magnetic field, there should be some spectrum of results of what happens. But actually, when you throw something like an electron through this Stern-Gerlach apparatus, what happens is that actually you either go up or go down. The electrons never go in between. They never behave like, it seems like the magnets are always oriented with the direction of the measurement. Okay? So it either go up or down. Now, if you take a helium atom, there are two electrons in its lowest energy shell. And by the Pauli's exclusion principle, they must be different in some way, and the thing that they are different about is exactly their spin. What does it mean? If you take one of the electrons, you run it through the measurement, and it goes up, the other must go down, and vice versa. Okay? And this is called quantum entanglement. So these two electrons are quantum entangled. Now, Einstein, together with Podolsky and Rosen, were very upset about this formulation. So this is like a mathematical formulation. There is some mathematical formulation of what this means, and they were disturbed. They said, no, that cannot happen. They must have decided beforehand in some way. There is some hidden variable. We don't understand something. Like something is still like, we need to still understand something extra, and then this weird mechanism will just be discovered as some what's called hidden local variables. Okay? Because what happens is that even if you take the electron to the moon and keep one of the electrons here, they will still do it. Like if you will orient the Stern-Gerlach apparatus in the same way, if the electron on the moon went up, the electron on Earth will go down, and vice versa. And they didn't have any time to communicate. So they can do the experiment like essentially in parallel, and they will still always like disagree on the orientation where they go. And that seems a bit confusing because it seems as if they are correlated somehow. And Einstein thought, yeah, correlation must mean some information has been sent between the two things. And it would imply some faster than light communication. Then came John Bell and said, actually, you can formulate an experiment. He started it with a thought experiment, but actually people started doing it after he devised the thought experiment, which is essentially structured according to a non-local game. So I'll tell you what a non-local game encodes. It encodes the following experiment that you can run in real life. So you have a referee, similar to what we had before. Maybe I'll start with a new board. So what does a non-local game encode? It encodes the following interaction between a referee, so that's the one that runs the test, the experiment, okay? And two labs. Okay? So the referee has access to two labs, lab A and lab B. Now first, the referee just has this mu, which samples an edge in the graph. So it's just probability distribution pi, mu, sorry, not pi. The referee pushes the mu, it gets an edge in the graph, right, as an output. So that's x, y. Then the referee sends to lab A only x, and to lab B only y. It then expects a bit string as an answer of some appropriate length. What is the length? Exactly the L function. So this lab A will send a bit string in F2 to the SX, and this lab will send B in F2 to the SY. Then the referee just decides either this is a winning condition or a losing condition. How does the referee do that? He evaluates the function D there. So D of XY evaluated on A, comma B. So essentially, this is just the rules of some interaction that someone running the experiment can do with two labs. Now, the whole point is that you can verify that the interaction is faster than light communication between the two labs. You put the labs very far away from one another, and then you can run the experiment, and you can just ask, what is the statistics of their winning probability? Okay? And let me give you a famous non-local game. Okay? It's called the CHSH game. The graph is just where this distribution is supported. Right? You can think of the vertices of the graph as the thing that you send to the labs, but the edges are exactly the things that the distribution is supported on. And that is important for some things in the proof, but at this point, it doesn't seem important that I have a graph structure. But I want to know what is the support of the distribution. That's very important. I'm forcing you, give me a graph, and then the distribution must be supported on the edges of the graph, okay? Great, so what is the CHSH game? So you have four vertices, A0, A1, B0, B1. Actually, it's better to call them X0, X1, right? Just because I said that XY is the X0, X1, Y0, Y1. And they are connected as follows. X0 is connected to Y1, X0 is connected to Y0. So it's the complete bipartite graph from the upper side. Oh, sorry, no, this is very wrong. This is still a yellow, but this is orange. So I have a graph. It has four vertices. It has four edges. I just need to tell you what is the distribution, what is the length, and what is the decision predicates. So all the lengths are 1. Okay, so whenever they answer, they just need to answer with a single bit. And I set a distribution. So uniform distribution, mu is uniform over edges. So with probability 1/4, I will choose any one of these distributions. And the decision predicate, if you have a yellow edge, is 1 if A is equal to B, and 0 if A is not the same as B. And the decision predicate, if you take an orange edge, there is only one of them, but is that we want the reverse to happen. So they will win if A is not the same as B, and they will lose if A is equal to B. So if I sample a yellow edge, I want them to agree. If I sample an orange edge, I want them to disagree. Great. Now, please tell me, if the world is governed by classical mechanics and they need to agree on everything beforehand, what is the optimal probability that they can win in this game? Yeah, 3/4, right? What would they do? Maybe give me that just. Okay, so if they always answer 1, they will always pass the yellow test, they will always lose the orange test, and it's a 75% probability of win, and you can show this is optimal. There are only 16 possibilities of answers, right? So you can just check all these 16 things and check that 75 is the maximum, 75%. It turns out when you use the formulation of quantum mechanics, you can get to 85%. And you can actually run this experiment in real life, and the 2022 Nobel Prize in Physics was given to people who, to Clauser, this first C here, and other, Aspect and Zellinger, for exactly doing such experiments in real life and showing that, yes, you can pass the 75% threshold significantly, and it just shows you that the world is not governed by classical mechanics, but by quantum mechanics. Essentially, entanglement is real. You can take it as this kind of what it demonstrates. Okay, great. So this is a non-local game, and I have only 3 minutes. Let me maybe quickly just tell you, yeah, I'm not sure that this would be too much helpful. So I didn't explain to you how, what is the formalism of getting this 85%. It's related to, I need to explain to you what does it mean to do a quantum measurement and stuff like that. In the notes that I sent, there's a very simple definition, which requires only to know what is the Fourier transform of a representation of f2 to the k. So if you know your finite representation theory and know what the Fourier transform is, essentially you know what a quantum measurement is. You can formulate everything in this language, and it's a very good language exactly because when you formulate things in the language of representations, representations and actions are closely related, right? Like, what is a representation? Is a homomorphism into UN. What is an action? It's a homomorphism into sim_n, and sim_n embeds naturally in UN. And essentially, this mapping uses this idea. Okay? Just the fact that the permutations are embedded in UN, and you need to be careful. You don't embed actually the permutations in UN. You embed the permutations acting on 2n elements in UN, and you do it such that they always encode some element that behaves like -1 and things like that, like minus the identity, which is a special type of unitary. But essentially, that's the idea of this theorem. And I won't say anything about this theorem. I think, I'll leave you to enjoy the CHSH game as my final remark. Okay, so I'm not sure that I understand your question, but this is just a game where the maximal, you can prove that if you use quantum strategies, the maximum that you can have is cosine. This is just cosine squared of pi over 8, which is approximately 85%. And the gap between 85% and 75% actually shows you that classical and quantum are different. But to actually achieve the 85% forces the measurements to be oriented in space in some way. And that is useful. Some version of this thing is used in our reduction. Yeah. But with another game, what's called the magic square game, and not this game. Just because 85 is not good. We want you want the quantum thing to be 100%. Einstein, Podolsky, and Rosen, the EPR paradox. Yeah, I'll write it. Einstein. I think Podolsky like this, and I think Rosen with an S, but you can check later. I'm not sure about the Rosen, if it's a Z or an S. Thank you all for coming and staying.